What are neural networks? Neural networks, also known as artificial neural networks or simulated neural networks, are a subset of machine learning, and the name is inspired by the human brain mimicking the way biological neurons send signals to one another.
What is linear separability of data points? If you can draw a line or hyperplane that can separate those points into two classes, then the data is separable. Neural networks use linear separability to separate linear data into groups. The data needs to be linearly separable to fix issues with wrong weight updation and wrong classifications of data. Now let us look at the XOR logic graph. If we look at the XOR logic graph, we can see that the hyperplane cannot separate our data linearly because the pink dot overlaps with the red triangle. This is why we use a multi-layer perceptron network or a neural network. We will have two nodes as the first input layer, each one of them being a value for the XOR logic. Now we will go over the code. First, we look over the structure, which has some necessary data needed by the neural network to function, such as the epochs, which tells the neural network how many times to train itself, and the learning rate, and all the nodes. Next, we have a few helper functions, such as the init weights, which generates weight between 0 to 1, the sigmoid function, which clamps the data from 0 to 1, and the derivative of the sigmoid function. Next, we have a function called activate network. This this runs for the number of epochs we have set in our network. First, we loop over the number of training sets we have, and then we set I is equal to the training sets number. Then we increment the bar to show the progress of how much our neural network has been trained. First, we use the activation function with the input layer and update the hidden layers. Next, we use the hidden layer as the input layer for the output function and use the same activation function for it. Now, we need to check for errors. We compute the delta error using the derivative of the sigmoid function using backpropagation, and then we apply the changes to all the weights in the output weights and the hidden weights and change biases accordingly. This way we can train our neural networks. The train function checks if the model.data exists. If this exists, it loads existing model state, which basically helps us load existing neural networks. Um, then we ask the user how many epochs we want this to run for. And then we run the network for that many epochs. Suppose the model.data does not exist. We create a new struct, save it, and then ask the user how many epochs they wanted to run. After it's done training, we just save the network, and that way we can load it back again. For the main loop, we just give the user two choices, whether they want to train or they want to run the network.
Now we are going to build this program using the cargo command with the release profile. We can check cargo.toml for the release profile, which is the optimization level true and LTO set to true. This will help us build the binary so that it runs really fast. Cargo build. This builds it for us. Now we can go to target, see release, and we can find our program here. We can execute it using XOR and then we can train it. Suppose we want this many epochs, and then we can run it. We can see our results are pretty accurate. However, just to give you a glimpse of the process, we can do something like this. We can train it, but only run it, say, 5 epochs. See, our results are very inaccurate from the actual output. We can train it for, say, 20 more epochs and then run it. It's still inaccurate. Say we train it for 500 times and then run it. 1,000 times run. It's getting closer and closer, I think. Suppose I train it for a straight of 10,000 times this time. It has gotten very close, and we can see how the neural network learns as it runs many times. So this is the working of the neural network.